Good afternoon, everyone. Jay McClelland, good morning to you. Jay McClelland is a cognitive psychologist and professor at Stanford University, where he's one of the founders and a current co-director of the Center for Mind, Brain, and Computation. And together with David Rumelhart, he arguably started the last AI summer in the 1980s with the two-volume book Parallel Distributed Processing, for which they received several awards, among which the Distinguished Scientific Contribution Award from the American Psychological Association and the EEE Neural Networks Pioneer Award. Good afternoon, Jay, or good morning for you. Thank you so much for joining this event. The idea of connectionism was a game changer for the field of cognitive science. For our viewers who are not in the field of cognitive science, could you maybe explain very briefly what the idea of connectionism entails?
The predominant idea in cognitive science when I was starting out in the field was that our knowledge was something we would think about as a set of propositional statements. Okay, all ducks have webbed feet, for example, would be something that we would think of as the nature of our knowledge about a semantic fact. Zebras have stripes. But if you wanted to actually recognize a picture of a zebra, that actually didn't help you, because your eyeball couldn't read the dictionary that had the propositions in it. So, well, what would be the actual system that the brain could use to sort of translate an image of a zebra into that's a zebra, right? So we thought, well, maybe a neural network could do that, because there could be connections from little features that represent stripes, let's say, that kind of connect up to a population of neurons that represents the concept of a zebra. And so where's the knowledge in that? Well, it's in the connections between all those neurons. And so that's basically what the idea of connectionism is.
Yeah, right. Thank you. So together with David Rumelhart, you put connectionism in the spotlight in the 80s with the two PDP volumes. But you've been working with spreading activation networks at least since 1977, as far as I could find in your CV when you were at UCSD. In the introduction to the new PDP handbook, you write that your understanding of PDP models came about largely through hands-on experimentation. But how did you come up with the ideas behind PDP? Did it just emerge from collaborations and discussions?
So when I was an undergraduate, I took a class in sensory mechanisms from a physiological psychologist, I guess, or a physiological vision scientist. And the field of vision has always been one of the places where the boundary between neuroscience and psychology has been less totally clear. In cognition, it's harder to know how you can use information from the brain directly. But in thinking about how neurons respond to visual information, you could do that experiment by shining light into the eye of an anesthetized cat, right? Or something like that. And so as an undergraduate, I was exposed to the basic idea that I was describing to you before, that a neuron could respond to stimulation by virtue of connections among from incoming neurons. And I, in the early 70s, I was a PhD student taking first exposed to cognitive psychology as a PhD student. Before that, I'd been exposed to animal learning, sensory physiology, and psychophysics. And I just sort of was always thinking, well, hey, we're thinking about this stuff so abstractly, but it's got to be implemented in the brain. So in 1975, I was invited to a conference, and I heard a talk by a man named James Anderson, who introduced me to simple neural network models that he was already using to think about aspects of perception and learning. And I was like, oh, we have a population of units that have connections to other units. I could represent this as a vector and a matrix. So the vector is the activations of the units, and the matrix is the array of connections. And now I can present a vector as an input and propagate activation through these connections. And that's when I started studying these things, as you say, by running simulations.
Right. How much of that work would you say, your initial work, was inspired by Minsky and Pappert's work at MIT?
I wasn't affected by Minsky and Papert at all in my case. In fact, Minsky and Papert were telling people that you shouldn't be connectionists, right? That their book essentially said, look, this connectionist idea that Rosenblatt is pursuing, Rosenblatt was pursuing in the 50s and early 60s, it isn't going to fly. That was the message that they communicated, and it created, what was I guess I would call a neural network winter from 63 when their book came out until, well, Grossberg was continuing on in that period, and Jim Anderson was continuing on in that period. So I think of those two guys as the only neural network researchers who were moving forward during this Minsky and Papert winter. And I myself was, when we started building models of perception, the interactive activation model, which was my first publication with Rumelhart, Grossberg was a very important influence on building our neural network. So Grossberg and Anderson were my inspirations, as well as the brain itself.
Okay, right. Well, so your PDP work originally meant to provide like a formal theory behind the neural implementation of cognitive phenomena, but artificial neural networks have been extremely successful in AI. Looking at the history of artificial neural network research, it seems to illustrate a very successful cooperation between cognitive scientists and computer scientists. So like Rosenblatt that you talked about earlier, he was a psychologist and he developed the perceptron in 58, and then Minsky and Papert even mention him in their dedication of the perceptron book. And then in 86, David Rumelhart, your collaborator, a cognitive psychologist as well, introduced backpropagation, one of the most widely used training algorithms for neural networks. Did you or any of your artificial neural network contemporaries in psychology ever expect their huge success in AI?
Well, it wasn't my thought. I wasn't trying to do artificial intelligence. I was always interested in how the human brain worked. But, the PDP group, so Rumelhart, he was a mathematical psychologist. So his background was in mathematics as an undergraduate, and he went to Stanford in mathematical psychology, which was then, one of the areas in the department. It was, and got his PhD in mathematical psychology. And then when he got to UCSD, he and Don Norman were very inspired by what we now call good old-fashioned AI, all that propositional-based kind of thinking, and he got very involved in that. And so his book, he wrote a book called Human Information Processing in the early 70s, in which he laid out the use of early AI models to try to do language processing, for example. But it was around the time he was writing that book that he started to realize that they weren't working for him. And, I think he was one of the people who kind of understood that the contemporary AI research wasn't really succeeding to deal with natural human-like intelligence, like the ability to understand speech, for example.
Yeah.
Machine speech perception at that time was complete complete mess. But he was very inspired by what people were doing in that, trying to do in that field. And so I think he always thought maybe that these things would be relevant. And then Jeff Hinton was trained in artificial intelligence. And he was a postdoc with us due to Dave. He was essentially, officially mentored by Dave Rumelhart, but he was actually teaching us how to think about the computational approaches to optimization, for example, and so on, which have become very central to the AI approaches. So I would say that people other than me were thinking already at that time that maybe there would be applications, and I think they were a little disappointed that it was so hard to get, actual working AI models based on the work coming out of the 80s.
Yeah, right. So this PDP work of yours, of course, it's based on the human brain. Do you think that the human brain can give ongoing inspiration for the development of new AI techniques, or is the idea of parallel distributed processing as far as the analogy goes?
Well, I would say yes, and the question is, so what exactly should we look for?
Right.
I think the main thing we should never do is to tell ourselves, well, we don't think the brain is doing that, so we're not going to build that into our artificial neural network. I myself find that, one of the key breakthroughs I think that Rumelhart made in developing backprop was to not worry about whether or not he could figure out exactly how brains could be actually doing it, right? So in other words, you didn't have to be able to say, well, look, here's the brain chemical that's doing the back propagation or something like that before you proceeded with that. So I think, he always liked to talk about neural networks as brain inspired rather than brain constrained, or I like to think of them as brain informed. I think about what I know about the brain, and I use that to inform my thinking, but not to constrain it. So brain inspired or brain informed. But ongoing motivation. So, humans are still far better than any existing neural networks at all kinds of aspects of intelligence. And the question that we're asking in my group is, well, do we want to chalk that up to differences in architecture between the brain and artificial neural networks, or differences in the learning algorithm, or are we just not in a position yet where our artificial neural networks can have the kind of rich lifelong engagement with an actual sensory experience that provides the initial fabric that supports the development of our perceptual and linguistic abilities and our motor skills, and then sort of provides the foundation for later acculturation and learning. And I don't know the answers to these questions. The one thing I know is that I can't predict the future. So
definitely,
I think we should look for inspiration and information wherever we can, but not overly restrict our efforts in that way.
Right. Thanks. Well, your current work focuses on mathematical cognition, specifically from a PDP perspective. I find it extremely interesting, as it seems to integrate some sub-symbolic computations and symbolic representations. And one could argue that this is one of the big problems in cognitive neuroscience. Do you believe that mathematical cognition could be a foundation for more general intelligence? Or are you just interested in mathematics because you just like doing mathematics?
So I think of mathematical cognition as a very exciting sort of challenge for artificial general intelligence. I don't think that mathematical cognition per se is the foundation of all other forms of cognition, but I think that the achievements of Euclid and Einstein and Newton and so on, are the reflection of the actual capacities of brain-style computational systems that we've been studying, and to figure out how those systems could achieve, a new scientific formulation of ideas grounded in a set of formal statements, mathematical statements. It just seems to me like, if we could do that, nobody would argue that we hadn't solved the problem of intelligence, right? In fact, I was partly motivated to do this because people kept saying, oh yeah, these neural networks, they're fine for, perception. Like we said before, the visual system must be using a neural network. Surely everybody is going to have to accept that. But when it comes to, proving a theorem or deriving a new hypothesis or sort of conjecture in mathematics, the idea that neural networks might play a role in that was something that I think people could distance themselves from and say, oh no, that's this Cartesian thing, right? The body is a neural network system. Descartes was happy for that, right? He thought of it as little pipes rather than neurons sending electrical signals that didn't have electricity yet, but it was the same basic idea. We share that with animals, but the real thinking, that was something else, right? So I wanted my inspiration for thinking about mathematical cognition was to do the same kind of real thinking that Descartes did when he did math himself. And I think it's really exciting to be able to think about these kinds of questions. My main inspiration for this is a quotation that I found on a bench when I was taking a hike in a beautiful forest this summer. And it was a quote from Poincaré, which said, "It is by logic that we prove, but by intuition that we discover." And my way of thinking about this is that, we never would have had the breakthroughs of formal mathematics without logic. But we never would have had the question, well, or the idea that some sort of thing could be true without the intuition that the neural networks are going to provide for us here. And so I think of the formal systems, and this is where I'm flipping other people's ideas on their head. I think of the formal systems as being the creation of people striving to achieve clarity, and not the foundational characteristic of the human mind. I think of those formal systems as being things that people use to complement their intuition, and then they acquire expertise in using them. That's what we do when we go to university. Or maybe, students who are going to go to university start taking courses in high school where they begin to develop an appreciation for these formal systems. Right. It's actually some Dutch educators, whose names I won't dare to try to pronounce, who introduced the idea that it's only in the later stages of high school education at the beginning stages of getting ready for university, that students even come to appreciate what mathematical or logical thinking is. And it's not the natural mode of thought of. So that's what I'm interested in. How do we come to be able to think that way, and how do we then harness that together with intuition? So we're not just sort of sitting there, cranking out logic.
Right. All right.
Yeah.
Thank you so much, Jay, for clarifying your current work as well. Thank you very much for joining. All the best, and happy holidays.
Same to you.
Bye-bye.
Bye-bye.